All right. Yeah. Thank you. Thank you for the invitation. And so, yeah, I'm gonna be telling you about some of my work at the joint of these two areas. This talk is based on four papers with Ilias, Jelena, Haichen Dong, Shivam, Daniel, Shuyao, Alessio, Mahdi, and Steve. Okay. All right. So let's get started. So the main theme of the talk is to tell you about some recent exciting development at the intersection of these two areas. One is called robust high-dimensional statistics, and the other is called non-convex optimization. So what I'll do is in the first 10-15 minutes of talk, I will give you an overview of these two areas and then motivate some of the questions we want to ask at the intersection of these two. And then I'll tell you some math. All right. So robust statistics. All right. So let's look at perhaps the simplest statistical 101 question that we can in high dimension that we can think of, which is I want to estimate the mean of d-dimensional spherical Gaussian from samples. Okay. So I have this mu star, which is the only unknown parameter here, and nature draws me n samples from it, and give me these blue points, and my goal is to output a vector that's as close to mu star as possible. Okay. Now, this is a very well-studied problem. We know exactly how many samples we need if we want, let's say, accuracy epsilon. I know I need roughly d over epsilon squared samples, and yeah, so on and so forth. Very well-studied problem. The robust version of this is where robust statistics kick in. There are many versions of this. Today, we're going to focus on a specific version, which is adversary gets to corrupt epsilon fraction of the points. Okay. Right, so remove some clean blue points and add some red points anywhere he wants to. Okay. And the problem stays the same. Now you're given this remaining blue points plus these red points. Of course, you don't know the color. And your goal is still to output a vector as close to mu star as possible. Okay. Estimation. I want to be a little bit formal about the corruption model here because we can actually achieve. People usually ask me, "Oh, what assumptions are you making about these red points and so on and so forth?" So I want to be formal about that. So this is how the game goes: is your algorithm, a robust statistical estimator, first specifies how many samples it wants. I want n samples. Okay, and then nature shows up and draws you unclean samples from your ground truth distribution. All good. Now this adversary shows up, and here we allow the adversary to inspect everything. In particular, he can look at your code, look at the ground truth distribution, and look at the samples drawn by nature. Everything. And you can assume his computation is unbounded. There's literally no requirement other than he can replace at most epsilon fraction of this. All right, and your goal is to solve the original problem, but now under epsilon corruption. Question about the model? All right, perfect. So what do we know about this problem? So let me tell you some results about robustly estimating the mean of a d-dimensional spherical Gaussian, right? So statisticians have studied this problem. It goes way back to people like Huber and Tukey. But before maybe 10, 12 years ago, we know, like all the solution that we know for this problem, for robustly estimating the mean of a Gaussian, is either has dimension dependent factor in the error guarantee, or it doesn't run in polynomial time. Which was less of a problem for statisticians, but as computer scientists, maybe we love polynomial time algorithms, so we want to get better of both worlds, I guess. And the good news is that you can, and you can in fact do better than that. So in 2016, the seminal work came out that showed you can get dimension independent or nearly dimension independent error guarantees in polynomial time. And in the next several years, new results came out actually improved the runtime to nearly linear. So And by the way, all these algorithms have near optimal sample complexity. So what are the three metrics I care about in a robust mean estimation problem? I care about how many samples I'm using, what's my runtime, and what's my error guarantee or minimax rate, right? And we already have algorithms that can achieve near optimal guarantee for all these three criteria. Right. So we're pretty happy about this. And now the question is, what do we want to do in this talk? Okay, we want to build on this or somewhat tangential to this, and do something else. All right. So this is where we would this is where the talk would kick in, is to say existing algorithms are very nice, right? You can solve this problem in nearly linear time, but unfortunately, the algorithm are pretty complicated. It requires subroutines like matrix multiplication weight update, and there's some other approach that are conceptually simpler, but then it requires some parameters to tune. And the question we want to resolve for robust mean estimation in the context of this talk is to say, can I use gradient descent? I love gradient descent. It works very well in practice, although sometimes I don't understand why. But let's put on a practitioner hat for a little bit and just ask, okay, I like this problem, robust mean estimation, right? Can I solve it with gradient descent? We're gonna come back at this problem a little bit later, but this is a conceptual question we're all focused. All right, and now let me introduce you the second pillar of the talk, which is non-convex optimization. So neural nets are extremely successful in practice. But there's this gap between the NP hardness of in theory, non-convex optimization can capture NP hard problems, but in practice, people will just run gradient descent on it. It doesn't really seem to feel it that much, right? So one question you can ask is how to explain this gap, right? A very successful line of work in learning theory offers one possible explanation to this phenomenon, which is for many machine learning problems that they actually have additional structure in the non-convex objective function. I can actually show that all your lakes are equally deep. If you converge to usually a second order stationary point, that you can show that actually all of those are globally optimal or approximately global optimal. Okay. Here's some figure. Usually it's due to some kind of rotational symmetry or discrete symmetry that even though your function is non-convex, but as long as you run some kind of standard optimization method, and when you stop, you will be in a very good solution. Okay. All right. Cool. So now, all right. So it holds for a long list of problems. This is not. This is, I guess, how the initial several problems. This is how it gets started, but this is more 10 years ago, right? So the list grows longer. But now we can make this question more formal. Now that I told you a little bit about non-convex optimization, I can say that can I formulate robust statistical questions in a way such that all local optima are globally optimal? Because if I can come up with such formulation, then I know I just need to run some standard optimization method and we'll solve the problem. Okay. All right. So this is one question we'll be addressing in different contexts in this talk, right? And now let's visit the other direction. So this is essentially non-convex optimization for robust stats. Now I want to do robust stats for non-convex optimization, which is how can I now imagine pick your favorite machine learning problem, let's say linear regression, which I will give you tell you some math about it. Let's say now it's under a robust model where epsilon fraction of the input are corrupted. Now, can I still solve linear regression in presence of epsilon corruption? Okay, turns out I can. And okay, let me be a little bit more specific in case you haven't seen this before, right? So let me define linear regression. This is one version of linear regression, handpicked best for this talk, I guess, right? So I have n labeled data points, right? Each one of them has a vector, which is the feature, and a number, right? Let's say I'm trying to predict the price of houses and this summarize the square footage and location of the house, whatever, right? Cool. And I'm under this very simple assumption that it's just a linear function of x. Oh, this should be capital Xi. All right. Okay, how do I solve this? I can solve this in many ways. But one particular algorithm we're going to try to adapt to robust cases is the following, right? I run gradient descent on least square loss. Right. Now, what do I know about this function? This function is convex in theta. So it has a unique local optimum. As long as the gradient is 0, then I know that I've converged to the global, unique global. There's one local optima and one global optima, which is W, right? You can verify this in many ways. One way to do it is just to compute the expectation of the true gradient when X is drawn from Gaussian, or I guess any distribution where the covariance is identity. You know that if your gradient is 0, then you're at global optimum. All right. Now, what we want to do next is we want to ask, what if epsilon fraction of these pairs are corrupted? Corruption can happen in either X or Y or both of them. I don't care. And this is still under the same model. You can look at everything, right? I have no assumption on how the corruption is given to me, as long as it's at most epsilon fraction. Now, kind of the punchline is I can solve this problem in the following way. I can look at my loss function as the average of n functions. Therefore, my gradient, my true gradient is, or my expected true gradient is the average, is the true mean of some distribution. So, right, so basically, I need to be, imagine I'm standing at some point theta, right? Because this gradient is only well defined if I pick a point theta. Once I decide where I'm standing at right now, this is a fixed distribution. You draw X from Gaussian, this defines a corresponding distribution, right? I claim without corruption, these Li derivative of Li theta is just clean samples drawn from this distribution, right? But now I have corruption, but that's fine, right? It's just my the empirical gradient I observe is an epsilon corrupted set of samples drawn from this distribution. Okay. Now, this is where I lied a little bit, is because this is not necessarily this is not a Gaussian distribution. It's more like a chi-square distribution, right? But trust me that you can also solve this problem. You can solve robust mean estimation for this distribution in particular, right? And then happily ever after, right? Because I can, if I just call robust mean estimation algorithm in a black box manner, in fact, I can get a vector that's close to the true gradient, which is close to this. And as long as I have a vector that's close to this, I can run gradient descent out. Okay. Questions? So what did I just tell you? I told you how to use a robust mean estimation as a black box to solve robust linear regression. Oh, you can probably notice that I did not really use anything specific about robust linear regression per se. Like, at least conceptually, this can just be lifted to any machine learning problem where your loss is no longer least squared loss for linear regression, but some arbitrary loss function, right? What I said is still true. Like the the actual gradient from the sample are epsilon corrupted set of vectors drawn from some distribution. And if I can estimate the true mean of that distribution, I can run gradient descent. Okay. Now, as long as my true objective function has no bad local optima, this would work. Okay. All right. So, but this is all done before us, and I'll tell you more in 30 to 40 minutes about how we want to do build on top of this. That is the idea, right? And right, so let me wrap up the intro part of the talk, which is I want to tell you a tale between these two research areas. On one hand, I want to develop new algorithms that solve robust statistical questions using gradient descent. with the hope that these algorithms may not have the best asymptotic runtime, but maybe they are easier to use in practice, right? In the other direction, I also want to develop a unified algorithmic framework. I want to solve a lot of machine learning problems under one framework that allow me to handle epsilon corruption for all of them. All right. Any high-level questions before I dive into the math? Cool. All right. So So I have three results prepared. So first, I'm going to tell you how to solve robust mean estimation. Then I'm going to, this part's the longest. Then I'm going to spend about, this part will be 20, 25 minutes probably, and then 10 minutes for each of the 10, 15 minutes for each of the latter things. Cool. Yeah. All right. So I want to solve robust mean estimation with gradient descent. Okay. Now, let me give you a little bit of background on robust mean estimation. So let's look at the 1D case to begin with. So for the univariate case, I want to connect the first moment with second moment. This is an important structural lemma for robust statistics. That says if you want to corrupt the mean of a distribution, a mean of a Gaussian, you have to corrupt its variance as well for 1D case. Okay. Here's intuitively why. This is essentially a Cauchy-Schwarz that if I want to shift my true mean by delta, but I have control only over epsilon fraction of the samples, right? I need to put them relatively far away because their total weight is epsilon. They need to be at roughly distance delta over epsilon away from the true mean. This way I have enough influence, right? But once I do that, they will create a bigger impact on second moments, right? Because second moment was square them and then weight them by epsilon. Right? So to change my mean by delta, I need to change the variance by delta square over epsilon. You can already tell that, for example, when delta is constant, right? If I want to move my mean by 0.1, then I need to move my variance by roughly 1 over epsilon, which is very large. That I can detect, right? Okay. So I'm skipping the formal math, but this is the punchline I want you to remember, which is if I can remove some samples, for example, then after I do that, my empirical variance is good, then I know my empirical mean must be good. It's a contrapositive of this statement, right? Okay, and now it turns out this analysis, this argument, can be generalized directly to high dimensions. What do I mean by that? If I project a Gaussian distribution along any direction, I get a one-dimensional Gaussian, right? So what that means is if the variance in every direction is what I expect it to be, right? For a spherical Gaussian, then I expect the variance in every direction to be roughly 1. Right? So if the variance in every direction is approximately 1, not too much larger than 1, then I know for this high-dimensional problem, my empirical mean must be good. So essentially, everything I told you here holds for vectors. All right, perfect. So this motivates the following natural objective function for high-dimensional robust mean estimation. Okay, I want to define some notations. So now xi are vectors. This is the weighted empirical mean and weighted empirical covariance of underweight W, right? Remember, xi are epsilon fraction of the xi are corrupted. Right, so key structural lemma in this seminal work is to show that is the following, right? So say if the spectral norm of sigma W is close to 1, then mu W is closer to me. The proof is essentially Cauchy-Schwarz, which I won't dive into. But it motivates the following natural objective function, right? I want sigma W to be close to identity because that's the true covariance matrix, right? So I might as well just minimize some kind of norm of their difference, right? Subject to a constraint that I cannot concentrate too much on a particular sample. Okay, intuitively, what does this constraint mean? It's the convex hull of all the indicator vectors for sets of size 1 minus epsilon. I want to capture all the, what's the intended solution? The intended solution is to put weight 0 on the bad samples and put uniform weight on the remaining 1 minus epsilon n samples. So this is a set that captures all possible such weight vectors. It's a convex hull of those vectors. All right. So what do we show in this paper is we show that just if you just run gradient descent on this object function intuitively, if you run gradient descent on this, you'll be fine. All local optima of this optimization problem will give you a good empirical mean. Okay. All right. So this is a slightly more formal statement. This is a non-convex objective. Right. Even for 1D, there's a simple example you can construct to show it's non-convex. All right. I want to sketch you a proof for this fact. So let me use W star to denote the intended solution, which is uniform weight among the remaining good samples. The way we prove this is not the first proof that we came up with, but it's a proof that I teach right now, which is shortest, but not necessarily conceptually easiest to come up with, I guess. But yeah, bear with me now, I guess. So I can prove you this fact that if Fw is for any W, if Fw is larger than what I expect it to be, right? So Fw can be a little bit positive due to concentration error, right? But if it's any larger than that, I can show you that no matter where you're standing at, moving towards W star will decrease the value of that. Now it should be clear if this blue statement is true, then I can prove this function, then that implies this function has no value. It's a very simple statement. It just says, no matter where I'm standing at, if my function value is above this bad threshold, then I kind of have a cone to the global optimum, or to the intended global. I walk there, I will go there. All right. How do you prove this? You just write it down. You can write this in, explicitly. So if I'm currently standing at W and let's pick a very small eta, right? A tiny eta, and move just a little bit towards W star, right? You can write down this holds with equality. This is like the covariance of a mixture of two distributions, right? You get a linear combination of their own covariance plus some third order, plus the third term. That's the outer product of something related to the mean of these two distributions. All right, and we can show you a lemma that says this third term will be dominated by the second term, and therefore this is true. If I can somehow magically ignore the third term, then what I said is true, right? I essentially get a linear combination of these two things, but I know this is pretty good, and this is not so good. So I'm taking interpolation between them. Therefore, my objective value would go down. Okay. Now, formally, how do I ignore this third term? Is I can prove to you this fact, which in spirit is exactly what the structural lemma is trying to say. Remember, we proved earlier, I sketched to prove earlier, to show you that if the empirical covariance is close to identity, then the empirical mean must be small. This is essentially that statement. I guess this statement implies that structural result, but it's a bit more powerful. Okay. But now you can take spectral norm on both sides of this, and then use triangle equality. The spectral norm of the third term can be upper bounded by this, which gets absorbed by this term. So instead of 1 minus eta, you will get 1 minus eta plus 4 epsilon eta. But epsilon is so small, so you get at least 1 minus eta over 2, for example, and therefore your objective value would go down. Yes.
What is delta?
Delta is good. The question is, what is delta? Delta is a lower bound, I'm assuming, of this. This result only holds when this is large enough. If this is very close to 0, I don't have this.
But for gradient descent to work, you need to compute the gradient, right? So
yes,
that's essentially saying when you set eta to be like very close to 0.
Good. So the question is about the value of eta and how it relates to gradient descent.
Yeah.
Yes, right. So this is a structural result. So far, don't think about algorithm yet. This eta is not the learning rate. This is something else, although it's named eta. Right? It just says I just want to use it to prove this blue fact.
Yeah, but moving towards you are talking about this one, like this directional gradient being positive.
Yes.
And you can prove that.
I can prove that by taking the limit when eta goes to 0. I can compute the gradient by taking eta. Yes. That is exactly right. All right, cool. Questions? Simple proof. I think the hardest part for this is to realize this would work. Somehow we just never. Yeah, it took us some time to actually try this. We were trying something more something fancier than this, and it turns out this is sufficient. All right. Okay. Now there's a little bit. There's some intricacy to this where I will explain now. So the spectral norm of matrix where it's parameterized by W may not necessarily be differentiable with respect to W. So so you need to handle this issue. There are a few ways you can handle this. One is you can run subgradient descent, right? So you can, in each iteration, find a vector that maximizes the, you can find your top eigenvector and then do one standard gradient descent in fixing that direction, right? Or you can do some kind of softmax. You do this trace of x of your eigenvalues, and then now it's differentiable, right? Both approaches work. And this is roughly what your algorithm look like. Either you do some kind of projected gradient descent. I guess you always do some kind of projected gradient descent, but your gradient can be different depending on how you want to handle this. And the analysis, if you are well trained in optimization, is pretty standard. You can prove that this converges linearly and so on. All right. And you can implement this as a MATLAB code that I wrote. We have several GitHub repos in several papers that call this as a subroutine. It works reasonably well in practice. So one of my long-term goal is to say whenever people are doing some kind of coordinate-wise median, when they want a robust solution, I want them to run this instead. But we'll see when we get there. Right? All right, question about this part. Awesome. So now let me tell you a little bit about sparse mean. So for robust mean estimation, we're lucky in the sense that we look at the most natural objective function that kind of already being examined in the literature, and it kind of just worked. But in some other for some other problems, we need to invent an objective function that did not exist before in the literature. And I'll tell you one such example. So this is a problem called sparse mean estimation. And I'm going to alleviate myself of a lot of detail by still focusing on Gaussian distribution. But now I am promised, so it's still the same problem, except I'm now promised the ground truth, the true mean is k-sparse. I'm given k, I guess, right? And I want to study this. This is a clean version, but I clearly want to study the robust version of this problem under absolute corruption. First, I want to tell you a little bit, just give you one motivation for why am I interested in the sparse case, right? People are interested in solving this problem in practice because sparsity is amazing. It allows you to get away with much fewer samples. For the traditional mean estimation problem, there's an information theoretical lower bound of d over epsilon squared, right? But for sparse mean, there's an upper bound of k, roughly k squared log d. So you should think of k being roughly log d, right? So this is polylog d, which is much smaller than d. The information theoretical lower bound is something like k log d. but we are not too concerned about this gap between k squared and k here. What we want to do is we already know how to solve this problem. Actually, one open problem is whether you can solve this in nearly linear time. I believe that's still open. But we know how to solve it in say quadratic time. Yeah. All right. And but the point of this talk is I don't care too much about runtime. I want to solve it with gradient descent. Okay, what do I do? Okay, robust version of this. Right. Same problem, but now the input is actually corrupted. And there's another problem which I won't define very formally, but yeah, you can ask other questions in the context of sparsity. But maybe for the talk, let's just focus on robust sparse mean estimation. All right. Now, same question, except this placeholder is now replaced with robust sparse mean estimation. Okay. All right. We showed that we gave a new objective function and showed that all its local optima, all its first order stationary points are a good solution for the original problem. I guess, yeah, and compared to previous work, our result works for a wider family distribution. Okay. Let me just tell you directly what the objective function is. So this is something that we designed, where I think the main novelty of the work it is. So mu w and sigma w is still the same definition as before. They're just weighted empirical mean and covariance. This is some kind of new norm on a matrix, which I'll define now. It's a Frobenius norm, but it has a bunch of restrictions on how am I computing this Frobenius norm. So it says I want to focus on the largest k-square entries with the additional constraint that I must choose k rows. And then in each of these k rows, I can choose k entries. And that's it. And I will motivate to this a little bit, but this is essentially the main contribution of the paper, which is to say, look at this new objective function. It turns out if you run gradient descent on this, you're fine. And if you run gradient descent on some of the previous well-studied objective function for this problem, it won't work. All right, what's the motivation? The motivation is the reason why I'm able to get away with much fewer samples is that I no longer need to certify in all directions. Right? Remember, for the original problem, I need to show that if I project my distribution along any direction, my variance is roughly 1. If I can guarantee that, then my empirical mean will be close to true mean, right? But for sparse mean estimation, I only need to certify this for the sparse directions. I also only need, consequently, I also only need concentration in the sparse directions. That's why I can get away with a much smaller union bound and require much fewer samples. All right, so in particular, the objective function is motivated by this requirement. Is I want this to be an upper bound for all quadratic form that look like this, for all sparse mean. Okay. And you can kind of quickly do a sanity check of why this is true, right? This can be converted into an entry-wise matrix, entry-wise inner product between two matrices. One is sigma w minus identity, and the other is VB transpose, right? But VB transpose is a matrix that only has k squared non-zeros, and that's distributed in k rows, and each row has k entries. And that's why I designed the objective function to look like this. Okay. And the magical part is actually this is also you can actually show landscape results. Cool. Yeah. All right, a quick sketch on how do you prove this. It turns out you just pretty much take the original proof and it will just go through. Except, okay, this is the old thing. I haven't changed anything. I've told you this before. You can prove a structural lemma like this that allows you to ignore the third term. And this holds directly after that. Now, how do you prove landscape result for this objective function in the context of sparse mean estimation? You prove a different structural lemma that replaces this spectral norm with FKK norm. Okay, that requires some additional work, but not too much. And then the whole the high level sketch of the proof remains. Yes.
So you define the norm to be like k rows, and every row you choose
K entries.
k entries, but they may not align as the same k columns.
Yes, they don't have to align.
Yeah, but from the analysis in the previous slide, this VB transpose is just like a strict k by k block.
Yes.
And it's even like symmetric.
Yes.
So you did a relaxation here.
Yes. So the question, right? The question, if I understand correctly, is to say that motivated by this property, I should really I can further restrict this norm. I can invent a new objective function, let's say f prime w, right? Which says these k entries also needs to be aligned in each row, right? Good.
And I think they are even symmetric. Like you choose the indices of rows, and
Yes.
that has to be the indices of columns.
Yes. The question is, how about that objective function? Right now, I have a different candidate objective function. I guess my first the first comment I want to add for that is, how do you compute such a norm? If I give you such a matrix, how do you compute it?
That will be my question as well.
Yeah, okay, good. The question is, how do you compute this? Let's take a look. It's a great question. How do I compute this norm? Let's look at this first. Okay. Well, if I know, I can compute the for each row, I can compute the largest. I can define something called the L2K norm, which takes a vector instead of outputting its L2 norm, I output the L2 norm with largest K entries. Right? Now I can compute the L2K norm of each row, and I can pick the top K row. That's how I compute this, right? But for the objective function you proposed, it's unclear how you would compute it.
Yeah, but it's the local optimal characterizations remain the same.
Good, great question. I don't know, but I suspect the answer is yes. But you can see we have some other objective here is we want to actually be able to compute this rather than having it be a NP hard problem. It's probably some reduction to planted clique or something that right, there indeed is yeah, I think so. That for some matrix you cannot find, yeah, this is the densest case of graph, for example, right? So yeah, that's why it is, I believe the object function you propose is NP hard compute. But you're right, the landscape result is separate from the algorithm side of this. Okay, cool. By the way, the previous objective function for this in the literature that people use are, for example, f k squared. They said instead of adding this additional blue constraint, I just have the first row. Okay, and it turns out that is sufficient for some other algorithm, but not for gradient descent. That objective function has bad quality. But if you are solving SDP to minimize it, then you're fine. And, cool, yeah, fine. Great question. Right, that's all I want to say about the first half of the talk. Any more questions before I move on to the second part? Yes.
So you mentioned how to compute this at K norm. You
Yes.
asked that you compute this gradient.
Yes.
How do you compute the gradient?
So great question. So intuitively, the earlier two approaches would both work. One is the simplest to think about is probably just subgradient descent. Like I'm standing at some W, right? I can compute sigma W, which is not too fast, but I can compute it, and minus identity, right? Then I have an explicit matrix. I know how to do this. Then I essentially have a mask, right? I can run one step of gradient descent with respect to this mask. So you can also smooth this by doing some kind of softmax. But I think subgradient descent is easier to analyze. Yes.
What class of distributions do these algorithms for, like beyond Gaussians?
Great question. So the question is, I can do this for Gaussian, but what about other distributions? For mean estimation, you can solve this problem as long as your true distribution has bounded covariance, and that's necessary.
bounded, like as in the spectral norm?
For example, you know the covariance, the true covariance is in PSD order Atmos identity.
Okay.
All these are typed.
And the error you get is like this epsilon times square root of log.
No, you get square root of epsilon.
Square root of epsilon.
Yeah, so great question, by the way. So I won't go back because too many slides back, but the information theoretic lower bound, even for Gaussian, is epsilon. But I don't have this square root of log of epsilon. There are lower bounds that says that for any statistical query algorithm that you have to suffer this root log of epsilon. And there are SOS algorithms that can that works better for for other distributions. Yeah. So amazing question, but not in this talk we just focus on Gaussian. But ask me offline about all these amazing other distributions. There are extensive literature on this. You can in fact ask this question for more general things like mixture of Gaussians and so on. You want to robustly learn a mixture of Gaussian distribution when your sample are epsilon corrupting. Sorry, you don't need epsilon corruption in that case because you have multiple Gaussians and you're more in the listed codable side of case. But amazing work. There are many amazing work in the context of robust statistics, and I'm just showing you a tip of iceberg here. So we're really focusing on the easiest problem in robust stats and ask how can gradient descent help solve those. But of course, you can ask this question for harder and more challenging and more delicate, tricky to solve problems. All right, cool. Okay, now let's move on to the second part of the talk, which I now want to use robust stats to help solve machine learning problems under this epsilon corruption model. Okay, this has been done previously. People have already had this idea of implementing robust gradient descent. And that works for many problems. You have to analyze it a little bit carefully, but everything's fine. Okay, the motivation for this talk is there is this obvious gap between the existing literature before our work and which is essentially the following, right? For many machine learning problems, including just all these basic ones like matrix completion, phase retrieval, and so on, just getting your gradient to be 0 is not enough. It's enough for linear regression because it's convex, right? But in general, I'll show you an objective function which comes out naturally from phase retrieval. In general, you really do need to your Hessian to be PSD. If the only thing you know is gradient is 0, that's not enough to imply you're at a global optimal solution. But in many cases, as long as you add the second order condition, as long as you can escape all the saddle points, then you're fine. Okay. And there's this obvious space here, which is to ask, can I compute a second order stationary point for my favorite machine learning problem? Okay. Because if I can do that in the presence of epsilon corruption, then I'm golden for these problems. And then I solve the epsilon corruption version of these problems. I will show you two work which kind of provides two different solutions for this problem. One is also how, by the way, how landscape analysis for a lot of non-convex ML problems started as well. So initially, we don't really know how to prove a global landscape result. We always initially, for the clean version of these problems, we also went through these stages in the sense that sometimes I can show after a good spectral initialization, I have no saddle points. I run gradient descent, I want to be at a saddle point. And later we can prove global things, right? But yeah, okay, two results. So two solutions. One is, let me just initialize close enough to a global optimal solution. I have many global optimal solutions, right, due to symmetry. But if I get close enough to one of them, then there's no saddle point in that region. Okay. All right. Or you just, I guess, look at your, try to robustly estimate your Hessian, and then you're fine. Okay. But then you need more samples and it's computationally more expensive. Okay, let's look at the first example problem. This is a problem called phase retrieval. So let me define this. It's usually defined in the context of complex numbers and Gaussian vectors, Gaussian sensing vectors. It has something to do with observing the intensity of light over a duration of time is much easier than observing as a function of time how the intensity of light changes. Right? So X-ray Christology and so on. Right? So it's an important problem. But now we're going to look at an abstract version of this where the AIs are real Gaussian. And the unknown here is X. So I'm trying to recover X. And I'm given Gaussian vectors and the corresponding intensity measurements. So I don't have, in linear regression, I just have this term, but in phase retrieval, at least at a very simple conceptual level, I just have, I have no sign information. I just know the magnitude of this. Okay. All right. Now we want to solve the robust version of this problem where epsilon fraction of the AI-Y pairs are arbitrarily corrupted. All right. Now this is the main theorem. It says we can do this, we can solve this problem in nearly linear. All right, but that's not so important. What's more helpful is probably look at this objective. We didn't invent this. This is again a very natural objective function for phase retrieval. So what does it do? I am going to write down a loss function at for a vector z, right? Eventually, I want z to be equal to x, right? That's when yi is going to, if z is x, this will be 0, right? So I'm taking the difference between this and I'm doing least square on this. But this is now a fourth order function, a degree 4 polynomial of, degree 4 is degree 4 in z now. And it turns out for this function, just having its gradient equal to 0 is not enough. This function has saddle points. 0 is a saddle point, but you have some additional saddle point that's very nice to teach. So if you teach non-convex optimization, this is a very cool function to teach. You can actually write down the gradient and Hessian and see why there are saddle points. But if you require the Hessian to be PST, you will get rid of them, right? Okay. Now, what do? Is we show that if you initialize close enough, even though this is a non-convex function, under epsilon corruption, you can still initialize close enough to a ground truth distribution in nearly linear time by solving what's called a Kaifan K-norm SDP. So that's not important, but basically there is a way for you to very efficiently initialize into a point that's very close to ground truth. Precisely in this sense, right? So the L2 norm between my Z1 and the ground truth X is at most some constant. Here we're normalizing the norm of ground truth to be 1. All right. Question about the result? Yes.
So can I go back?
Yeah.
Oh, so I wonder about the question in discrete case.
Okay.
So let's say X is a binary string, and the computation is X is like over some finite fields,
Sure.
F to the D, and the computation is over these fields.
Okay.
Does your algorithm generalize to that case?
No, I don't think so.
Okay.
Okay, but I'm happy to talk more offline. This algorithm heavily requires on it actually it uses the property of Gaussian. So. It has no lattice flavor or anything. It's a pretty continuous problem. All right, cool. So right, the other way you can get around this, which is relevant in some other problems. So I don't think this is the final result, but it is one way that you can solve a lot of ML problems under one framework. So what you do is you can, in addition to robustly estimate the mean of a distribution, you can also robustly estimate the covariance of a distribution. You now have additional assumptions, and you require the force moment to be in some connection. The force moment needs to be related to second moment in a certain way for this to work. But you can do it. You need these square samples. But this is a problem that I really should have defined on this slide, which is called low-rank matrix sensing. So for that problem, I don't really know how to solve it when epsilon fraction of the input is corrupted. The only way I know how to solve it is by doing this, by robustly estimating the Hessian. So what is this algorithm? You essentially just run robust gradient descent, right? You run robust mean estimation on your empirical gradient. At some point, the robust mean estimation algorithm is going to return you a vector that's very close to 0. Then you say, okay, I'm happy. I know that with respect to the true objective function, I am at a approximate first order station point now. That's when you would call a Hessian oracle to robustly estimate your true Hessian and see if it has any negative directions. And if there is, then you would go in those directions. Right? So this is a standard second order optimization method that just looks at the Hessian. Right? And also imported code for this. And okay, good. But why do I not like this result so much is because the sample complexity is not tight. For matrix sensing, we know that even under epsilon corruption, the correct information thread lower bound only has one D in it. It doesn't have D squared in it. It's more like D times poly rank or something. Which means this is really too big of a hammer that you're using to solve this problem. If you want to say, I want to look at I need enough samples so I can see the Hessian clearly under epsilon corruption, then that's too strong of an ask. If you ask that, you are going to end up with the wrong sample complexity. It is necessary under some cases, but in general, yeah, there is an open problem. Yeah. All right. Cool. So now let me wrap up with some open problems. So first question is, I showed you solution to robust mean and robust sparse mean for the first part of the talk. Can I use gradient descent to solve other robust stats tasks? In particular, the problem, even for covariance estimation, is open. To be fair, there is a work by Jacob Steinhardt and his group that showed there is an objective function where all local optima are approximately global optimal. But that objective function, computing the gradient of that objective function requires you to solve semi-definite program, which we don't like. Everything I showed you in this talk, the gradient can be computed via some kind of direct, simple algorithm, like looking at some matrix and vectors, and then you can get it, right? So I guess the open question is, can I have a simple function that works for robust covariance estimation? I have some ongoing work in this area, but I'm not good enough at SOS, so I haven't solved it yet. But we'll see. I also don't want an SOS algorithm, but we'll see. All right, so okay, and then you can ask this question of what if I want gradient descent, the simplicity, the conceptual simplicity of gradient descent, but I also want near optimal runtime. The algorithm I showed you does not run in nearly linear time. This gradient descent thing. So I basically sacrificed asymptotic runtime for hopefully practicality. But really, I would want to achieve both simultaneously if I can. Right? I don't know how. Some version of matrix multiple gradient update or gradient mirror descent should probably appear for this. Also for this, we tried to implement this. It didn't work out very well. That's because even computing this matrix takes too much time. If you have d square samples, each of d-dimensional, d is, let's say, 100. Computing this via fast rectangular matrix multiplication is already too slow. So we don't want to do that. Okay, so if you just have Frobenius one here, you can get around this by using some iterative method. You don't have to write down this matrix explicitly to compute this one, usually. But because you're focusing on this k by k thing, you have to write down this explicitly. So we don't really know how to get around that, but it would be pretty exciting to be able to get around that. Because in sparse problems, the number of samples you have is so little, right? So you really don't want to compute a d by d matrix. The number of samples you have is like log d, right? So okay, anyway. All right, and then in the other direction, right? I want to identify more. So I showed you phase retrieval, I showed you matrix sensing, but there are many problems out there. Tensor decomposition, neural nets, that I want to ask the same question for how can robust stats help? Right? I think it's especially interesting for two layer in the NTK regime for neural nets and so on. Right? I don't think that question has been resolved yet. Okay, you can try to do find a robust second order state treatment without Hessian. So there are work out there that shows converging to saddle point actually is a very fragile thing. If you just perturb your gradient, as long as you don't live in this thin layer of green things, you would diverge in the direction you want to diverge. And you want to be stuck at this saddle point, you actually just oscillate your way out in the negative direction and you'll be fine. So the question is, can I solve, I guess, matrix sensing in the epsilon corruption model with the right sample complexity by doing something along this? All right, and that's it. Thank you.